So today's topic is 8.3, graphing rational functions. Our objective for today is to sketch graphs of rational functions on Desmos and identify key features of their graphs. Those are our main topics. You will demonstrate this on the exit ticket, the quiz, and then the unit test. All right, so let's do a little bit of an overview. First, I'm going to go over some definitions and some examples, what that kind of means for our problems. And some more definition work, all that good stuff. Then we'll go into a couple problems where we'll find out how to find the points of discontinuity, which is one of our vocab words. And then we'll go into how to find vertical asymptotes, which is another one of our vocab words. Then lastly, we'll talk about actually graphing those and seeing where that happens in our graph. Then you have a couple of you-do problems at the bottom and an exit ticket at the end. That's kind of the overall plan for today. Let's start up at the definitions. So first off, again, we're talking about rational functions, the same thing we've been talking about this whole unit. Rational functions are anything with the function on top and bottom. So any type of x on top, any type of x on bottom. Okay. Here's what the three kind of things that you will see. You'll either see the function look something like this. We'll see why that is in a second. You'll have a function that looks like this, where it's just a regular graph with some hole in the middle. And you'll see one that's more like this, which is the one that you'll most commonly see, right? Where you have two diverging kind of lines. Right? So those are the three type of graphs that you'll see in these problems. This one right here, let's start with it, comes from the fact that this denominator, when I set it equal to 0 and solve, I get x squared equals -1. X squared equals -1, which means that x equals plus or minus the square root of -1, which is I. Right? Since it's x equals plus or minus I, since the solutions to the bottom, the problem with the bottom would be imaginary numbers, and imaginary numbers aren't on our coordinate grid. There's no imaginary point anywhere on here. There's no point where we're going to have a hole or anything. It's still going to have this weird graph like this. All right. So that's your first example of something that can go wrong. Right? This is what that'll look like. When we have some type of denominator, or when we set it equal to 0 and we solve, we get imaginary solutions. Right? That's really what we're going to be seeing right there. On the second one right over here, this type of graph is going to happen when we cancel out the top and bottom, these x plus 2's, and we end up with a regular function, no actual rational function. And so it'll just be x plus 3 in the end. Again, that's because the x plus 2's cancel out. And so we end up with our graph at x plus 3. We plot the point 3, down 1/1, all the way down here. Now we have our line. All right. But we can't have a certain point on here, specifically when our denominator equals 0. So if our denominator x plus 2 equals 0, means that x equals -2 is going to be a problem. All right, because we cannot have a 0 in our denominator. And so we have a hole where x equals -2. All right, we have a spot where it does not exist. No, let's draw circles right now. See if I can do this. There we go. It's kind of a circle. All right. So that's kind of what we have to do. This is what this happens. This one happens when we cancel out, and then we have a hole. The last one over here is what happens when we have something that doesn't cancel out. You'll see as the x minus 2 does not cancel out with the numerator above. So then when I set that equal to 0 and solve, I get x equals 2. And so we will have what's called an asymptote right here. Let's use our nice line right here. Starts up here, goes all the way down. All right, and an asymptote, again, we learned this last semester, but let's do a little refresher since it's been a while, is a line where it gets ever so close to it. My graph gets so close, so close, so close, but it never quite touches it. Yeah, as close as humanly possible without ever actually getting there. All right, so that's what an asymptote is. And again, that happens when I set it equal to 0, I solve, and I can't cancel out. Before we move on to kind of giving things more of a formal definition, are there any questions on the 3 different types of graphs that we'll see? This weird kind of like diverging one, this one right here that just became a line, or this kind of diverging curves. Anybody have any questions on how we got any of these graphs or anything like that? All right. Let's move on. We'll talk about this with the words that we're going to be talking about with our definitions. So we have 2 different words right here that we're going to talk about, continuous versus discontinuous. They're pretty self-explanatory. Continuous means that it keeps going, it continues on forever. Discontinuous means that at some point it breaks. So this first graph right here would be an example of a continuous graph, because when I put my pencil on this graph and I start drawing it, I never have to pick up my pencil and go on forever that way. On the other hand, over here with this graph, when I'm drawing it, I start here, and then I have to stop because there's a hole right here, and then I have to continue on after that. So this would be a discontinuous graph because of the fact that it has that break in the middle. This would be an example of a continuous graph because it continues on forever, all right, without any breaks. This right over here, since when I'm graphing it, I get that same break in the middle. I have to go down here, then I have to stop, come back up to the top and draw this part of the graph. Means that it breaks. So this one again will be discontinuous. All right. Are there any questions between continuous versus discontinuous graphs? Again, I won't know if you're having a question unless you tell me. Do you need me to repeat anything? Re-explain something? Go back over everything? Anything? All right. Let's move on to points of discontinuity then. So we've gone over continuous versus discontinuous. Now we're going to talk about the actual points of discontinuity. We have 2 types that we're going to be talking about. We're going to talk about removable versus non-removable. In the case of removable, those are the ones that I can cancel out my equation. All right, so this would be an example of a removable discontinuity. Another word we like to use with removable discontinuity is hole. Right? We have a hole in our graph, we call that a removable discontinuity. Right? An example of that right there would be all the way over here. That point right there. We can see that in the problem when that thing cancels out. So since the x plus 2's cancel out, it's going to be a removable discontinuity. All right. Let's put that as well. Let's actually type that in. So instead of writing it out, let's actually type that in. Now the word for this is whole. There we go. And another thing that we're going to talk about is when the denominator cancels out. Except we're going to capitalize for the proper person when the denominator cancels out. So since it cancels out in these two, this is going to be a removable discontinuity. Right? Over here, the x minus 2 did not cancel. And so this one will be an example of all the way around non-removable discontinuity, also known as an asymptote. Okay. We'll also use the word asymptote a lot. Again, the non-removable discontinuity happens when I can't cancel it out. The denominator doesn't cancel. All right. That's what that means. Are there any questions on what a removable discontinuity or a non-removable discontinuity are in terms of this? Someone asked a great question. Someone asked, why can you explain why the whole is at 2 again? So again, it's at -2. Specifically because I set this denominator, we'll see later on, we set this denominator equal to 0 and we solve. So we go x plus 2 equals 0. So x equals -2 when we solve that. And so at x equals -2, there's going to be a hole right there. Same thing over here. If I solve this equation, set it equal to 0 and solve, I get x equals 2 in this case. Since I can't remove it, it's a non-removable, it's going to be this one right here, this line. So again, we solve the denominator for 0 because that's where the problem can happen. When my denominator equals 0, when I'm dividing by 0, that's where we have errors. Are there any more questions on this before I move on? Be a great thing to do. Maybe take a screenshot real quick, just so you have this, in case you didn't actually write it down on a separate piece of paper or something. Another thing to make sure you did is to type anything that I typed in that was extra. All right, so let's go kind of do some problems now on how to actually use this stuff and all that, using these words. Our drawings, we're going to move down now. We do practice. So this first one right here, we're going to be finding points of discontinuity. So remember, there's two types of discontinuities, removable and non-removable. Remember, removable in my graph looks like a hole, while a non-removable looks like an asymptote. Removable cancels out, non-removable doesn't cancel out. Right, so that's what we're looking for. To find what cancels out and what doesn't cancel out, we first need to factor our function. So we factor the numerator and the denominator right here. The x plus 3 is already factored. And then we just need to factor our denominator of x squared minus 4x plus 3. When we do that, we could use our x method, two numbers that multiply together to get 3 and add to be -4, are -3 and -1. All right, so we put that -3 and -1 down there. Now that it's factored, I got to see if I can cancel anything out. Because if I cancel it out, now it's a removable point. If I can't cancel it, then it's a non-removable. So we're trying to check to see what type of ones they are. X minus 3 and x minus 1, nothing cancels out since these two don't actually match. This one has a plus and this one has a minus. So if we're checking things off, we've done this. We can't do this one because there's nothing to cancel. And so since nothing canceled, this one's done as well. So now I'm going to state, oops. Since the x minus 3 and the x minus 1 don't cancel out, they will be non-removable discontinuity points. That's because, again, I didn't cancel them out, top and bottom. I couldn't do that, so they are non-removable. Now, in the chat, I would like everybody to tell me, what's another word for non-removable that we had above? What does non-removable mean to us as well in the case of a graph? You can tell me in the chat. It's 1 for 1 so far. Correct answers. Good, 2 for 2. You can tell me what non-removable, what's another word for non-removable in our, what we've gone over so far. All right, 2 for 2 so far. Let's see if anybody else can tell me. Yeah, is it sleeping today? All right, perfect. We're gonna move on. Asymptote is the word. Perfect. So a non-removable discontinuity point, another word for that is an asymptote. So these are both going to become asymptotes in the end. So now I set each one equal to 0 and I solve. Right? X minus 3 doesn't equal 0, x minus 1 doesn't equal 0. X equals 3 or 1. And then I like to, you don't have to technically, but I like to restate what it is. So x does not equal 3 and x does not equal 1 are non-removable discontinuity points. And again, they are non-removable because they didn't cancel out. Since they didn't cancel out, non-removable. Also known as an asymptote. Are there any questions on problem A before I move on to problem B? Remember, does anybody need me to repeat anything, go back over anything, any specific area someone wants me to focus on? I'm confused about how you got x minus 3 doesn't equal 0. Where did that come from? I'm confused on how you knew it was a non-removable discontinuity versus a removable one. I still don't know what that means. Can you re-explain it? Anything along those lines? All right, then we'll move on. We'll do the same process. Factor first. Factor the numerator and the denominator to get x minus 5 times x plus 5 on the denominator. There's a couple different ways that we could factor that. We're having problems with that. We could use our x method, or we can use our difference of two squares property. The x method is I'll put negative 25 at the top, 0 at the bottom. Two numbers that multiply together to get negative 25 and add to be 0 are negative 5 and 5. So that's where I got my negative 5 and 5 from. Now I need to notice that I can cancel my x minus 5s on top and bottom. So then I'll get y equals 1 over x plus 5. Can anybody tell me, based on what we just did, based on the fact that we just canceled this out, what type of discontinuity point will x minus 5 be? All right, will it be removable or non-removable? Someone tell me in the chat, a couple people, as many people as possible, please tell me in the chat whether this x minus 5 is removable or non-removable. We got 2, 3 correct answers, 3 for 3 so far. Anybody else want to make a guess? Again, it's better to guess and get it wrong than to stay silent and think you know what you're doing. Someone want to make a guess. Is it removable or non-removable? All right, good, getting a couple more. This right here is a removable point, just like a lot of people said, because of the fact that it cancels out. So since these two cancel, it's going to be removable. All right. The other one doesn't cancel out, so it's going to be non-removable. So that's stated right here. Let's restate it. Since x minus 5 canceled out, x minus 5 is a removable point. Since x plus 5 didn't cancel out, x plus 5 is a non-removable discontinuity. Right? Now we set each one of those equal to 0, or not 0 to be specific, and then we solve. X minus 5, x plus 5, 5 and negative 5. This is where I like to restate my problem. X does not equal 5 is a removable point, and x equals negative 5 is a non-removable point. Are there any questions we did on how we did B and the factoring and the canceling before you try C down below? All right. I'm going to let you all try C right now. I'm going to clear my screen in a second. And we're going to move down to C. I'd like all of you to try and complete C. Once you're done with it, you can put your answer in the chat. I'm going to give you 4 minutes to do this. Let me know if you have any questions. I'm here to help. Which is the vertical asymptote. Again, we've already gone over how to find the vertical asymptote above when we talked about non-removable points. Because non-removable points and asymptotes are the same thing. Asymptotes just talk about what happens on the graph. Non-removable points talks about what happens inside the function. Right? So like in this case, we have an x minus 2 and an x minus 3 right here. Since they do not cancel with the numerator, we know that these two since they do not cancel out, they are vertical asymptotes. All right. Again, that's another word for non-removable discontinuity points. So now I set them equal to 0 and I solve. Finally, restate my problem, all that stuff that I told you to do, you get your answer. X equals 2 and x equals 3. Now notice that I have these written as equal signs this time. That's because we're now talking about an actual line on a graph. So usually we use actual equal signs. Like if we go to our Desmos right over here, you'll notice that this line is an actual equal sign. You can't use the not equal and make that a line. All right. Are there any questions on part 1 of example 2? Any questions on how I found my vertical asymptotes, how I knew that they were both vertical asymptotes, anything along those lines? All right. Let's do this problem now. I'm going to do that same process we did above. I need a factor first. See if I can cancel anything out. I factor to be x plus 3 times x minus 2. I notice that the x minus 2's cancel, and so we get 1 over x plus 3 in the end. Now, when I'm talking about vertical asymptotes, all I care about is the one that doesn't cancel out. Since x plus 3 doesn't cancel out, it is a vertical asymptote, so x plus 3 equals 0. Again, I skipped the x minus 2 because it is not a vertical asymptote. Instead, it'll be what's called a hole. Right, I solve this problem, and I end up with x equals negative 3 is a vertical asymptote. Are there any questions on this process of factoring, canceling, and then finding your vertical asymptotes? So it's a great question. Someone asked, will the asymptotes always be vertical? The ones we find this way will always be vertical. I'll show you another way to find the horizontal ones, but I'll show you that in a second. Right. We're going to start with the vertical ones. So there doesn't seem to be any questions on this. We're going to follow this along right into our graph. So I'm going to go over to this Desmos page right here. So we have a couple things that we have on this graph. If you plugged in your graph from this problem, it's x squared plus 4x minus 12 over x squared minus 4, your Desmos will give you this right here, right? Just this graph right here. This will give you partial credit on any time you turn in this as a graph for whatever it's asking. To get full points, you will need to label the vertical asymptote, which we had right here, any removable points, and then any horizontal asymptotes. All right. For the vertical asymptotes, to get this x equals negative 2, I need to do exactly what we did before and factor this. All right, so I factor the numerator and denominator, and I get x plus 6 times x minus 2 over x minus 2 times x plus 2. Again, that's my difference of two squares and my x method being used. I cancel out my x minus 2s, x minus 2 and an x minus 2, and I end up with x plus 6 over x plus 2. So now I can use that information I just got to be able to graph my function a little bit better. We know that x plus 2 is going to give us a vertical asymptote since it did not cancel out. So we'll do that math over here. X plus 2 equals 0. We solve and we get x equals negative 2. So my vertical asymptote is going to be right here. X equals negative 2. All right. Again, we got that one because it did not cancel out. Vertical asymptote. On the other hand, we had one that did cancel out. So that's going to be our removable point. So we'll take that one right there. We'll do that math as well. X minus 2 equals 0. X equals 2. So I go to where it says 2 on my graph. I go up to my point, and I put a hole right there. Right, a little dot right there that shows that it is missing. Right, and that would be my first part of the process, finding my vertical asymptote and finding my removable point. We've already shown that. Are there any questions so far on how we got our vertical asymptote or how we got our removable point? I would also like to mention before you ask any questions, I forgot this part, we will always be graphing with Desmos for the most part. And if you're not graphing with Desmos, it'll already give you the graph. or it'll be on Math Excel where you can use their program. All right. You'll never have to hand draw one of these graphs, really. It's a great question. Someone asked me, can you show me how I did the removable point? I'm going to exit out of these ones and show you how I create them. Right. So first thing, I have this x equals -2. So I'm going to plug that in. Very simple. It gives me that graph. Now, I don't really like that it's a solid line, so I'm going to hold it down. If I hold down this little circle, it'll give me the option to choose whatever I want. I like the dash line for it. I just feel like having green today. I can change the width of the line, the spacing of my dashes, all that stuff. And so I'm going to choose this. That's going to be my line. For the point, I go over to and I go up to it, and I see that this is kind of where it kind of ends. If I wanted to be exact, I could plug in 2 to this function right here, see what I get out, and it'll give me my point of 2, 2. And then I like to label it. All right, I'll call it either a removable point or the other word that we use, a hole. Again, just like before, I hold this down. I go to where it says this open circle, and I choose whatever color. I think the black makes it kind of stand out more, so I chose that one. You can also make it a draggable point by doing that, which is kind of cool. We won't need that. Last thing is we have our axis of symmetry across this one, which is going to be y equals 1. And again, I hold that down, make it dash. I like to make it match so that it looks kind of nice that way. And so. Does anybody have any questions on anything else? Maybe how I actually got those points, how I know that each one is removable versus non-removable, which one was an asymptote, all that type of stuff. Anybody need me to re-go over any of that stuff? Remind you how to do it, any of that? All right. Now let's go over how to get my y equals 1 line. The main way we do that, actually, let's give everybody a chance to, if you would like to, you can take a screenshot of this real quick so you have this for reference. I'll give you a second to do that. All right. So to get this right here, there's 3 different cases that we kind of got to go through. I'll clear this now. I got this graph of y equals 1 by taking my leading coefficients, the x squared and the x squared, and dividing them. The reason we do that is because we're really kind of taking the limit as something goes off towards the highest number possible. So this x squared term is really going to start deciding what's happening. All right, so I go y equals, and then that fraction, x squared over x squared. The x squared's canceled out, and so we end up with just 1. So that's how we got our horizontal asymptote right here. All right. Again, I took my leading coefficients and I divided them. Now, as another example of something that could happen, let's say that instead we had a 2x squared over 3x squared. All right, as our 2 functions. I would do the same thing, y equals 2x squared over 3x squared, and I would end up with 2/3. Right? So that would be another way, that would be another example of how I would get my horizontal asymptote. Divide my two leading coefficients. Whatever's left over is my horizontal asymptote. Now there's two other options that can happen. The other one is if they aren't equal. All right. So let's say that the denominator is bigger than the numerator. So I have a x squared over an x cubed. Whenever we have this and we simplify, we'll get 1 over x. And how this is going to work is that we got to think about this as going up to infinity. We have 1 over an infinitely big number, which gives us pretty much 0. And so our line right here, our asymptote will be at y equals 0. That specifically again happens when my numerator's power is smaller than my denominator's power. Right? Lastly, when it's the other way around, we have y equals x cubed over x squared, let's say, we end up with just a regular x. There is no horizontal asymptote. All right. So those are the three examples, the three different things that can happen with a horizontal asymptote. You can have them be the same, and then it's whatever they divide to be, whatever the coefficients are. You can have the denominator be greater, in which case it'll be 0. Or you can have the numerator be bigger, in which case it's no horizontal asymptote. Are there any questions on these horizontal asymptotes and how to find them? This would be another great one to take a screenshot of. All right. Doesn't seem to be any questions, so I'm going to leave you all to do the you-do problems and then the exit ticket and all that. Let me know if you have any questions. I'll be here to help. Good luck.